We're still talking about triangles. Today we're going to talk about some special segments in triangles. There's five that we're going to talk about today. And they're just lines that we can draw inside of any triangle to give it some special properties. So I have like 5 definitions for us we're going to get through today. Nothing too terrible. Starting with one that we should already be kind of familiar with. It's an angle bisector. An angle bisector divides an angle into 2 congruent angles. The angle bisector can be a ray, it can be a segment, or it can be a line. Most of the time, what we're going to see are segments as our angle bisectors. Now, if I take a look at this triangle ABC, the angle bisector will always start at the vertex of the triangle. The vertex is any corner. Doesn't necessarily have to be the one that's like the most on top, because just depends on the way your triangle is drawn. So any corner is where they start, and they're just going to go down and divide that angle in half. So let's say I put this point as point E, then AE would be the angle bisector of that triangle. Is that good? Fantastic. So if I look at this diagram, we're going to get real familiar with this diagram. We see it about 4 times. I want to name a specific triangle that contains an angle bisector from the figure at the right. So I am specifically looking for, where do I see a line with 2 congruent angles on either side? The only place that I see that in this diagram, I'll give it to you for the first one, is here and here. This segment AE is the angle bisector of that triangle ABF. Make sure we have good notation. We're using the triangle symbol for triangles. We're using a line on the top to indicate a segment. Any questions on that? Number 2 says, in triangle DEF, EG is an angle bisector. And then we have some angle measurements. We're finding the measure of angle X, we're finding the measure of X and of angle DEF. So what we should be doing here always is starting with a diagram. I'm going to draw, it doesn't really matter, any triangle DEF. That was a terrible triangle, but it's okay. We're going to pretend it's fine. And then I say, okay, EG is my angle bisector, which means E, the point here in my triangle, better be a part of that angle bisector. Now I'm going to draw the line so that it looks like it's bisecting that angle like it should. So wherever it looks like is about halfway between our angle, that's where I'm going to put my angle bisector, and here's where I'm going to put G. Anytime we are drawing things in a diagram, we have to make sure that they have the correct labels and tick marks. So for this specific one, I need to make sure that these 2 angles are marked as congruent. Now I can just start filling stuff in. So I know that GEF is this angle over here for x minus 20, and GED is 2x plus 14. What equation can I set up for these 2 angles? They're congruent. Caitlin? Perfect. So I can solve for x. It's not too bad. I think I get 34 equals 2x, or 17 equals x. I have to plug it in to find DEF. That's the last part of this problem. DEF is this entire angle at the top of my triangle. So I'm just going to plug it into one of the sides and multiply that by 2, because I know that they're congruent. 2 of them make up that whole angle. So the measure of angle DEF is 2 of, let's say, angle GED, which is 2 times x plus 14. So this is 2 times 34 plus 14 is 48. So this is 96 degrees. Any questions on that? That's our first vocab word, angle bisector. It's the only one that cuts an angle in half. The next vocab word, maybe this one is new for us, is a median. A median of a triangle is a segment with endpoints, again, beginning at the vertex. So it has to begin at one of the corners. And the other endpoint is going to be the midpoint of the opposite side. So if I take a look at the opposite side, think about opposites like you draw an arrow from one side to the other. Its opposite end is the midpoint of that side, meaning that each piece of that base are congruent. So that right there would be my median. Let's call this point M. AM is the median of triangle ABC. Again, notice it's starting at a vertex. It's cutting that side in half. I know nothing about angles when I'm talking about a median. The only thing I know is that this base is cut in half. So kind of like the opposite of an angle bisector, right? Angle bisector, we only know angles. Medians, we only know about the sides. One way that I remember, median, midpoint, they both start with an M. That's what I always think of. In number 1, it says name specific triangles that contain a median from this figure. Can somebody give me one example of a median? There's a bunch of them in here. You're looking in this diagram for where two pieces of one side are congruent. What if I start you off and I give you one of them? How about if I tell you, if I look at this entire triangle, ABC, then CD is a median because it bisects that segment at the bottom there. D would be my midpoint. So your first example is triangle ABC, where CD is a median. Can somebody give me another one? Any median. Allegra. Perfect. This triangle right here has a median right here because these two pieces are congruent. So triangle AFC with FG as my median. Perfect. Can I get one more? Aubrey. ABF is this guy right here. Do we know AE is a median? AE? We don't know that. That's an angle bisector. Tells me the angles are congruent, but we don't know anything about those two sides, so we can't say that they're congruent. Give me another one. I don't think there is one in ABF. What else we got? Casper? Perfect. Okay, same triangle we had before, ABC. And then let's go with AF this time. So a different vertex that I'm starting with, but I know that these two sides are congruent because they both measure 10. So that AF is a median. Perfect. Any questions on that? We got to be careful looking at those tick marks, making sure we're not making stuff up. All right, next page. Our next vocab word is an altitude. Have we heard that word altitude before? In a context other than a math class, maybe. What does altitude mean? Dahlia. Perfect. Like the height of something. Maybe you've heard it when you're talking about like an airplane or something like that, right? Its altitude is its height. Specifically in math, an altitude of a triangle is a segment from the vertex, once again. These first three all start at the vertex. And it contains the opposite side to the line containing the opposite side, and is perpendicular to that side. Can I spell? Maybe. Okay, so I need you to imagine an airplane for me for a second. I'm going to draw my little diagram here with my airplane on the ground. Let's imagine that my vertex that I'm going to draw my altitude from is A. I'm going to imagine that that's a little airplane. My airplane drawing skills are off the charts, by the way. That's my little airplane. The opposite side to your airplane is the ground. That's like your opposite side, whatever. Now think about when you measure something's height. Let's say I wanted to know what the height of this little magnet here is. I am never going to measure my height like this. I'm never going to slant it. It is always going to make a right angle so that I can measure height. I never measure height slanted. You shouldn't. So when I measure the height of this airplane to the ground, I need to make sure that it makes a right angle. So my ground doesn't just stop where BC is. My ground is going to continue on this way so that I can measure from that airplane straight down to the ground, forming a right angle. That line in red there that I'm creating, let's call this AX, that is my altitude. Hello? Altitude. Does that make sense? So sometimes my altitude is outside of my triangle, and that's okay. Other examples of this, sometimes my altitude is inside my triangle. It comes from a vertex straight down, right angle. Sometimes it's inside. Sometimes, if I have a right triangle, where do we think my altitude is? It's going to be the side of that triangle. So 3 different ways that an altitude could look and all be true. We could have one on the outside, one on the inside, and one that is a side. So when I look here, oh, hello. In number 1, I'm looking for altitudes. There are so many in this diagram. Can I have a few of them? Anybody? All I need is a right angle, Presley. AE is an altitude for what triangle? ABF. Perfect. Let's continue this. AE is also an altitude for what other triangle? Anna. AEF. If I have a right triangle, it can be its own side. Can I get one more for angle AE, or for segment AE? Maybe one that's showing where it's on the outside of that triangle? Any ideas? Caitlin? AEB would be another one. I'm going to put it next to this one because it's also like a right triangle, right? AEB. Okay, those are both sides of that triangle. What about this one right here? AFC. FC is that base, right? That's my ground. I have to extend the ground a little bit to get the height of that triangle. So it's on the outside of my triangle, but it still works. So triangle AFC also has altitude AE. Okay, let's move away from AE. Give me another altitude. Any of them? Caitlin? Perfect. FG is right here. For FGC, this right triangle. Let's keep using FG. Give me another triangle that works for FG. Anna? AFC, the whole triangle. Can we do one more? I think we can. Casper? We did FGC. Go the other way. FGA. Perfect. Okay, any questions on that? Let's draw a little picture. American Airlines Flight 5501 takes off from Mitchell, heading to St. Lucia. The airplane has a ground distance of 1,300 miles from Milwaukee with an altitude of 30,000 feet. I'm going to draw a picture. When I'm talking about altitudes, typically I'm always drawing right angles. Typically, I'm going to draw a right triangle. So let's draw my little picture here. I'm going to put my plane up here. They're leaving Mitchell. Oh, gosh. My planes are getting worse today. There it is. Its altitude is 30,000 feet. That means to the ground, it makes a right angle, 30,000 feet. Ground distance, that's talking from the airport to right below where the airplane is, 1,300 miles. I don't have to solve anything here. That's just a picture. Questions on altitudes? Okay, a couple more. The next one is a perpendicular bisector. We have also seen this term, I think, at least once before. We've definitely seen both of these terms separately before. Perpendicular bisectors are the only ones that do not have to start at a vertex. A perpendicular bisector, you can probably guess from the name, is a segment, line, or ray that bisects a segment and is perpendicular to that segment. Again, it does not need to begin at a vertex. They can, but not always. So let's take a look here. We're not going to be naming the triangle. We're just going to be naming a side. So let's take side AB, and let's draw the perpendicular bisector to AB. That means I'm going to bisect the segment, so cut it in half. Let's call that M, because it's the midpoint. And then I'm going to draw a line that is perpendicular to that line at point M. So it's just going to go straight up and form a right angle. Again, notice it's not touching a vertex. It doesn't have to. Sometimes they do, but not all the time. Any questions? So if I'm looking at number 1, name a specific triangle that contains, this one is name a side and then name its perpendicular bisector. I have to look for 2 things. I have to look for a right angle, and I have to look for 2 pieces of a side that are congruent. Well, I look at this right angle right here, and I don't know that BE and EF are congruent. So I'm going to move away from there. Over here, I know these 2 sides are congruent, but I don't have a right angle. The only place that both things are true is right here at FG. It is a right angle to AC, and we can tell by the tick marks that it's cutting AC in half. So FG is the perpendicular bisector to segment AC. Any questions on that? Okay, I have a secret 3rd page for you, I'm sorry. The last special segment that we are going to see is called the mid-segment. Now, the mid-segment gets a bunch of special properties. The mid-segment is kind of different from the 4 that we've talked about so far. The mid-segment is the segment that connects the midpoints of 2 sides together and is parallel to the 3rd side. So that's our first property, that it's parallel to the 3rd side. And our second property is that it is half as long as the 3rd side. So in my diagram here, I am saying that DE is the mid-segment. I know it's a mid-segment because the definition of mid-segment is that it connects the midpoint of one side to the midpoint of the other side with a segment. Then I get 2 properties. The first property is that it is parallel to that 3rd side. The second property is that it is 1/2 the length of that side. That's it. Any questions? So you're going to see a lot of diagrams that look like this. You're also going to see weird ones that look like examples 1 and 2. So in number 1, it says use the midsegment theorem to find angles. We are looking for angle DBE, that angle right there. We are told ADF is 55, and we're told that DF and EF are going to be midsegments. So let's think about what those definition of midsegment is. I'm going to focus on DF here. Ooh. If DF is a midsegment, that tells me that it is the midpoint of each of these sides, which doesn't really help me because I'm looking for angles. But it does tell me that DF is going to be parallel to this base right here, BC. So these two lines are parallel. Then how am I going to fill in this mystery angle over here? Any ideas? Aubrey? How do you know? Yeah, this becomes a transversal. These are parallel lines. So therefore, this angle and this angle are corresponding angles. Parallel lines imply corresponding angles are congruent. So that angle, DBE, is 55 degrees. Any questions on that one? Okay, let's do the same thing over here. We're going to, again, use my diagram where D, E, and F are the midpoints of the sides. So if I'm told that a point is the midpoint, I'm going to go ahead and mark all of that information up. That means if I connect my midpoints, I get a mid-segment. So if I'm looking for what is DE, I'm going to connect those 2 points up. I now know that DE is a mid-segment. And how am I going to set it up to figure out what my measurement of X is and then what DE is? What formula am I going to use here? Or what property? It's right here. By definition, by our midsegment theorem, our midsegment is 1/2 the length of that full side. So DE is 1/2 the length of GJ. I hate to use 1/2 times anything because then you get 0.5s all over the place. So instead, I always just do, pro tip, 2 times 4x plus 5. 2 times the midsegment is equal to 1 of the long segments. That just avoids any decimals. So 8x plus 10 equals 3x plus 25. I'm going to do some subtraction here. 5x equals 15. X is 3. I got to go plug it in to find DE, which is 4 times 3 plus 5, or 17. That's it. Any questions?